Okay, so today we'll discuss the young tablets. So the purpose of learning this young tablets technique is to construct the higher dimensional representations for a given group using the lowest dimensional representations. For example, consider SU2, which is a special unitary group of rank 1. And as you know, this group also represents the angular momentum or the spins. The representations are, you can think of like two-dimensional, 3, 4, 5, 6, and so on. They have dimensionals. Okay. So now the idea is whether we can construct this higher dimensional representations starting from 3 using the lowest dimensional representations, or in other words, we call them fundamental representations, which is 2. So how do we construct them? Them is here, and the other higher dimensional representations apart from 2. Now you might be wondering that why the higher dimensional representations are important. So in the context of quantum field theory, which is also has some application in the context of particle physics, okay, there you might be seeing some of the words called the multiplet. What does it say? It say you can club some fields which have very similar kind of property. Okay, you can club them together, and that club contains more than one field, and that's what called a multiplet. Okay, now how many components are embedded within that multiplet is the dimensionality of that representation. For example, two-dimensional representations, it has two such components, and we know from the knowledge of isospin, which is also represented by the SU2, it has a plus half and minus half. These two states correspond to these two-dimensional representations. Similarly, for three-dimensional representations, you can represent the spin 1 particle which has three states like 1, 1, 1, 0, and 1 minus 1. And similarly, you can go for 4, 5, 6, and so on. So we need to analyze the property of these higher dimensional representations, but we need to first understand how they are being constructed. So before going into this young tableau technique, let's try to recall what we have learned in the context of angular momentum in quantum mechanics. So in quantum mechanics, we define the states in terms of J and M, where M is the eigenvalue corresponding to Jz, okay, and J is the eigenvalue corresponding to the J square. So J square and Jz commuting each other. So that's why we can define a good quantum number as J and M, and we can define a state by the Jm, right? So the question is, for a given value of J, how many states we can write down? We know that M actually is nothing but a projection of J with unit interval, right? So M goes from minus J to plus J with unit interval. So you can see whether it includes 0 or not, that depends on the value of J. If J is integer, 0 is included. If J is half integer, then 0 is not included. But in both cases, for a given J, there are 2J plus 1 number of states in between minus J to plus J. In other words, we can have 2J plus 1 number of Jm states we can write down. So we can say that for any given J value, there exists 2J plus 1 number of Jm states. So for given J, we can say it is spanned by 2J plus 1 number of states, and so the dimensionality of that space is 2J plus 1 dimensional. So now you can already get the, you have already gotten the idea and the dimensionality of the space with the angular momentum. So it's actually the multiplicity of that state. So we define D equal to 2J plus 1, where D is nothing but the dimension of the states, and we have to be very careful here defining this thing, that this relation is true if and only if for SU2. We'll see that the reason actually, one of the important reason behind using this Young tableau is to get some generic framework within this construction of the higher dimensional representations, and not angular momentum technique, because it is restricted to SU2 only. Now let's focus on the addition of angular momentum. We know that if we have two angular momentum, J1 and J2, so after the addition of angular momentum, you get different states starting from J1 minus J2 mod value to the J1 plus J2, right? So in the language of dimensionality, so J1 J1 angular momentum states is 2J1 plus 1 dimensional, and J2 is also 2J2 plus 1 dimension. So basically, we have two states of dimensionality 2J1 plus 1 and 2J2 plus 1, and you are taking a tensor product or the outer product, right? So now from there we get these states, and they are written in a block diagram form of that matrix. So which are basically individually 2J1 minus J2 mod plus 1 dimension and so on. And this is true for any value of J1 and J2. Now let's try to understand this theory with some example. Consider J1 equal to half and J2 equal to half. So you know that D1, which is basically the dimensionality of the space corresponding to angular momentum half, which will be two-dimensional. And same for the J2, which is also half, so D2 equal to 2. Now when you add this J1 and J2, we get this angular momentum 1 and 0. So now 1 contains these three states, 1, 1, 1, 0, and 1 minus 1. So that's why this spin 1 state is three-dimensional. 0 has only one state, which is 0, 0. This is a singlet or one-dimensional, right? So what we can say in terms of the dimensionality, that 2 cross 2 equal to 3 plus 1. Now remember, so this we have not employed here so far in a young tableau technique. This we have derived using this angular momentum. But it's because we already know the knowledge, we have already the knowledge of the angular momentum thing, so it's quite natural for us. Also, we can realize this thing in terms of the tensor product. So what you can say that, okay, so two-dimensional representation can be written as a vector like V alpha, let's say, and 2 bar, which is a conjugate representation. And for SU2, this 2 bar and 2 are the same because SU2 has the real representations, and this is represented by V beta. So this 2 cross 2 into tensor notation is basically V alpha direct product V beta, and from there we can construct a symmetric traceless tensor and a trace part. So we can single out this trace part, which has been singled out. It is basically delta alpha beta. So in terms of language of the dimensionality, this will be one dimensional, right? Because this is a trace, and the symmetric traceless tensor is basically it's a high dimensional representation. Now, if you use this alpha beta indices to be 1 to 2, and if you find out how many independent components in the stressless matrix, that you will find out to be 3. That's why you can see other way, that's a 3-dimensional representation, and the trace part is the 1-dimensional representation. So this is another way of looking into this tensor product. So now, what is this Young tableau? Young tableau is a diagrammatic approach to construct higher dimensional representation using fundamental and anti-fundamental representations. Okay, so what are these anti-fundamental representations? You consider them to be the conjugate of the fundamental representations. For SU2 only, because this is a real representation, so the fundamental and anti-fundamental representation, that is 2 and 2 bar, are same. So either we can write down 2 bar, or sometimes we just avoid writing 2 bar explicitly, we write it like 2. So now, what we'll do, we'll set up some kind of thumb rules for the SUN specifically, to get an idea how to construct those high dimensional representations and diagrammatically. Okay. So what I want to emphasize first, that before going into specific example, let me give you the generic rules, which if you can remember or if you can just follow, then you should be able to construct any some Young diagram. You can evaluate any Young diagrams for SUN. Of course, these are applicable for other groups like special orthogonal groups and so on, but that's beyond the scope of this particular course. So we'll not discuss this thing. For this particular course, we'll restrict to SUN. So now N is the fundamental one of the fundamental representations of SUN. So that is depicted by a single box. N bar, which is the anti-fundamental representation, which is depicted by n minus 1 number of vertical boxes. Okay, and a singlet representation is depicted by n number of vertical boxes. Now you can see one cannot have a representation which is less than a singlet representations, okay, which is unphysical, okay. And so for any given diagram, when you draw or you construct for SUN, at most in a given vertically we can put n number of vertical boxes. For SUN, n plus 1 number of vertical boxes or any number of vertical boxes more than n actually lead to some disaster or some wrong result. Okay. So now let's say we have this generic diagram which should look uh, like this. Okay. So I identified these to be as the columns C1, C2, C3, and so on. And let's consider there are n number of columns are there, and then from the horizontally there are rows are there like R1, R2, R3, R4, and so to Rm, where an m and n could be anything. Okay, so now we have to remember while constructing this or drawing this diagram, the number of boxes in Ri is always greater than equal to the number of boxes in Rj for I less than j. That means let's consider like let's say R1 and R2 here. Okay, so we can see that while drawing this generic diagram, I have kept the number of boxes in this row R1 is larger than R2, and number of boxes in R2 is greater than number of boxes in R3, but also number of boxes in R3 is equal to the number of boxes R4, which is allowed. But let's consider if you draw this kind of diagram where in the boxes in R1 row is 2, number of boxes in R2 row is 3, so this is not allowed. Okay, so this is one of the thumb rules. Now, about this column-wise organizing these boxes, we need to remember while setting up these boxes, we have to always fill them starting from C1, that is the first column. That means in the first row, if we have C1 and C2, so this C1 will be here and C2 will be there. So in the first row, R1 and R2, where we have these two boxes here. Okay, so we have kept one box at C1, another box at C2. But if we keep the next row that is in R2, if you have a one box only, and if we keep that box in C2 instead of keeping C1 to be vacant, and that is not allowed. So if you have one box, first you have to keep in the C1, and then if you have additional box, then you put in the C2, then C3, and so on. So we have to follow this cascade or the chain rule kind of thing. So the number of boxes in any column should not be more than n for SUN that I have mentioned already, because n number of vertical boxes implies there's a singlet representation, and one cannot have any representation which is beyond singlet, okay, which is less than singlet. The boxes in a specific row are symmetric to each other, while the boxes for a specific column are anti-symmetric to each other. And the notion of this symmetric and anti-symmetric is very similar to the symmetric and anti-symmetric property of the tensors. Like when you have, let's say, symmetric boxes, that implies basically a tensor where the indices are symmetric among themselves. Okay, because we have seen already one example where this can be depicted through a tensor multiplication also, but we'll see why do we avoid that and why that tensor product method is basically tedious and cumbersome and erroneous. So once we use these thumb rules to construct the diagrams, then our job is not done, because then we have to compute the dimensionality of those diagrams. So then how do we construct how do we compute the dimensionality of these representations? Okay. So let's say this is one of the generic diagram you find out, and you have to remember at this top corner left, okay, for SUN, we'll start with n. Okay, and then once we put n here, then we'll put some numbers in these boxes, and there are some rule we need to follow while numbering these boxes. If we start from n and if we go right hand side through a single row, we'll increase by 1 in it. Like this is n plus 1, this is n plus 2, n plus 3, and so on. Okay, and then we'll come back to n again, and then once we go downwards through a single column, okay, so we will reduce by 1 unit, that is n here, then n minus 1, n minus 2, and so on. So if there are m boxes, so we will reduce by m unit, and if you have n boxes horizontally for a given row, it will be added by the small n unit. And then we'll follow the same thing for each row. Like if you start with n minus 1 here, so increase by 1 unit, so it is n and then n plus 1. And if it's n, then downwards n minus 1. So in every angle, this rule or the numbering must be consistent. Then the dimensionality of this diagram is basically d, which we can write it down as a numerator by denominator. So now the next target is to compute this numerator and the denominator. So what is the numerator? Numerator is the product of all the numbers depicted in all the boxes. That is here, if you look into this diagram, you can see there are some numbers I have put inside n, n plus 1, all these numbers. So you collect all these numbers and you take product of all these numbers, and that will give you the numerator. So we will be describe this thing in detail and in a much more transparent way through some examples later. And then we have to calculate the denominator. So for denominator, we have to start from extreme right of the first row, okay, and then we'll draw a horizontal line from right to left, and then we'll stop at C1 of R1, okay, and then we'll draw a vertical line which will cross all the boxes which constitutes this column C1, and I will take an exit at the last box, okay. And say in this process I cross p number of boxes, so I'll put that number to be p, and I'll repeat that thing again and again for each row and each column, and I'll identify that counting, that how many boxes I'm crossing in the process. I'll collect all such numbers and I'll take a product of all such numbers, okay, and then the product will give me the denominator. So let me demonstrate through some example here. So let's consider this is a toy example or toy young diagram. So what I'll do actually to calculate the denominator, I'll start with this is the R1. So I'll go to the extreme right from here, and then I go horizontally to C1, and then I'll take an exit through the C1 like this. So you can see in the process I have crossed 1, 2, 3, 4, 5. So this will give me 5. Then same thing, I'll stop in C2, I'll take an exit. In the process I cross 3 such boxes, so this is 3 and this is 1, and so for R1 correspond to these 3 numbers 5, 3, 1, which I have collected here. Then I go to the R2, I'll draw the same thing for taking exit at C1, C2, and so I'll get the numbers 3 and 1, so I'll put this 3 and 1 here. And then for R3 I have only one box to cross here, so this is 1, so this is 1. So now I take a product of all such numbers, and that will give me the denominator. And remember the numerator and divided by denominator, the dimensionality is always integer, it cannot be fraction for validates, right? So now let's try to calculate or the construct some higher dimension represent from the SU2, and we'll also have an option to verify them through the addition of angular momentum. But we have to always remember this verification we can do only for SU2, and then we'll convince ourselves of the applicability of this Young tableau for the SU2, and then after validation we'll move to some other groups, for example let's say SU3, where we cannot employ the idea of the addition of angular momentum. So let's consider a two-dimensional representation which is depicted by a single box, okay, and the anti-fundamental representation which is 2 bar, which is equivalent to 2 because of this real representation. This is also single box, so you can think other way also, because for SUN n minus 1 number of vertical boxes gives you the anti-fundamental representation. So here the 2 minus 1 is single box, so this is also the real representations 2 bar. That's why, as I say, from the Young diagrammatically, you can see that the 2 bar and 2 are represented by the single box, and this is only true for the SU2. So now, for a first example, let's consider two spin hub states. If we add them, you get 1 and 0. In the language of dimensionality, this is basically 2 cross 2 equal to 3 plus 1. Remember, d equal to 2j plus 1, right? So now, if I don't know additional angular momentum, if I want to calculate the same thing using Young diagrammatic technique, so what we'll do, we'll construct this thing 2 cross 2 equal to is a tensor product of two boxes. And now we can keep this AB boxes horizontally or like vertically. Now you can see that they are basically indistinguishable boxes. So if I put B here and A here, so then actually this doesn't give you different structures. Or vertically, if I have A and B here, or if I change this B and A, it doesn't make a different boxes, right? So now if I have A and B, let's try to calculate the dimensionality of this thing. So this D equal to, so we first you have to give the numbering here. For the SU2, this is two-dimensional representation. So sorry, for SU2 you put 2 here, and then horizontally you increase by 1 unit, so this is 3. So the numerator is basically 2 times 3. Now to calculate the denominator, we start from here. This is only one row, so you start from here, you come and take an exit here, you cross two boxes and you take an exit here, so you get 1. So 2 cross 1, so D equal to 3. And now we have this vertical diagrams here. So you can put number 2 here, you reduce by 1 unit, so you get 1 here. So 2 cross 1 is the numerator. In the denominator, you take an horizontal line this, you take an exit like this, so you cross two such boxes. And similarly for the row 2, you can cross only one boxes. So this is 2 cross 1, so this is 1. So 2 cross 2 equal to 3 plus 1. So it is the same result with the angular momentum technique what you've done. So that you can see that Young Tableau technique can be verified for the SU2 in this way. So now to convince ourselves further, let's go to a more slightly complicated stuff where we are adding two spin one states. So so if you have two spin one states, if we add them, we get 2, 1 and 0. So this D equal to basically in the language of dimensionality is 3 cross 3 is basically 5 plus 3 plus 1. Now, how to write down the 3? So this we cannot immediately write down, but the previous task actually we can use to draw the respective diagram for three-dimensional representations, which is basically this one, right? Because we have calculated the dimension of this thing. And remember, this dimension and the diagrams may not have uniqueness, and that is much more, but that we will not discuss here, but that is just for your reference. So now we know we have calculated 3 and this Young diagram to be this. So when you calculate 3 cross 3 is basically product of these two boxes times these two boxes. Okay, so what we can construct that we can put AB and CD side by side. So we have four horizontal boxes. Then just below AB we put the CD here, and then we can put one C here, one D here. C and those CD here are basically symmetric. So I have told that AC are antisymmetric here, but because D is sitting here and then C is here, so we cannot say really the C and D are symmetric or antisymmetric. So this is allowed. Okay, so we cannot put D below C because then the CD will be antisymmetric, but initially the CD was symmetric, so that we have to be careful. Now the task is to calculate the dimensionality. So for if we take this thing, then you put the number for SU2, we'll start with like 2. So 2, 3, 4, 5, and then this is give you the numerator. We start with horizontal like this. You make 4 such exits and give you the 4, 3, 2, 1 numbers. So that's what we put it back. We get the dimensionality 5, and then we have this thing, and that actually gives you like 2, 3 vertically downward, so 1, then horizontally by 1 unit increase, so 2, and then you calculate this exit and then counter, so you get 2, 3, 1, 2 and 3, 2, 2, 1, so you get 1 singlet. That's another way of looking into singlet without even calculating this thing. So for SUN, n number of vertical boxes, this gives you the singlet structure. For SU2, if there are two vertical boxes, this gives you singlet. So you can see this is the two vertical boxes, this is singlet. There's another two vertical boxes, this is singlet, right? So this is obviously 1. So even before calculating explicitly, we can identify this to be singlet or one-dimensional representation. Now about this structure, we start with 2, so horizontally we can increase by 1 unit each time. So it's a 3 and 4, and then downward it's a 1. So the numerator is 2, 3, 4, 1, and then through the horizontally, if we come like this, take an exit, we get 4 and 1, and then 2 and 1 for this thing. So we get 3, right? So you get 5 plus 3 plus 1. Another way of looking into this thing 3, which again we don't need to calculate, if you just think smartly, that this is two vertical boxes, so this is singlet, right? So whether it's a singlet is attached or not, it doesn't matter. So you can remove this part virtually, and you are left with these two horizontal boxes. And we know that two horizontal boxes is nothing but the three. So this is another way of looking into this thing. So this is the way we can compute 3 cross 3, which is 5 plus 3 plus 1, and that is again can be, we have cross verified using this Young diagram technique. So now we have to see how, and this can be more useful. So as I told earlier also, that the notion of angular momentum and the related algebras are applicable for SU2 only. And this angular momentum addition method thus cannot be further used to construct higher dimensional representations for other SUN groups for, where n is greater than 2, for example SU3 and SU4. But Young diagram technique can be useful there for SU3 and SU4. So that's why the Young diagram technique is more generic method to achieve our goal, which is nothing but the construction of the higher dimension of higher dimension representations. Now let's see how do we construct this SU3. So for SU3, and the 3 is the one of the fundamental representations. So this is written as like single box. Okay, so now 3 bar would be n minus 1 number of vertical boxes. So that's this 2 vertical boxes. So now you can see immediately departure from the SU2 that this 3 and 3 bar are represented by two different Young diagrams, right? So now if you calculate 3 cross 3, it's a product of two such boxes. Okay, and then we can get these two such structures, and because we are working for SU3 here, so we have start from 3 and then to be 4. So this is the numerator factor, and the same way you construct the denominator factor, which gives me 6. And this is again the vertical boxes. So here for SU3, this will be like a 3 and 2, because downwards you actually decrease by 1 unit. So this is numerator 3 2, and denominator will be 2 and 1. So this is 3. So dimension of the representation is 3. But again, every time we have to be careful. Note that this is a vertical box, which is a completely antisymmetric object, or this is like a conjugate state, right? So that's why this is dimension is 3, but actually it is actually 3 represented by a 3 bar, and such that we can see this structure is nothing but this one. So this is a 3 bar, and so 3 minus 1, 2, now 2 vertical boxes there. So this is the conjugate representations. So for SUN, so n bar is the anti-fundamental representation depicted by the n minus 1 number of vertical boxes. So from that notion also we get the two vertical boxes for SU3 is 3 bar, and 3 plus 3 gives me 6 plus 3 bar. Okay, now you can see this we cannot use anyway angular momentum algebra to verify this thing, because that's not applicable here, and that is the beauty of the Young tablet. So we can calculate 3 bar cross 3. So 3 bar is depicted by this, 3 is depicted by a single box. So this box we can put here. So now, unlike SU2, this is SU3. So we can keep maximum 3 vertical boxes. So this is allowed, right? And we can put this attach here. We can't attach this thing here, because the number of boxes in R2 row will be more than the number of boxes in the R1 row, which is not allowed. So we have to attach here such that the number of boxes in R1 row is always greater than equal to number of boxes in the R2 row. Now these are three vertical boxes are there. So of course this will be 1, or you can explicitly cross check this thing to be 1, but I am not going to detail this thing. This is, you can verify this thing. Okay, and then we can calculate this part, which is as a, these two boxes symmetric among themselves. This box is anti-symmetric among themselves. This is like a mixed symmetric anti-symmetric property is there. So you start with SU3. So this is 3, and I'm repeatedly mentioning this thing, that what will be the number here, it depends on what group you are working on. SUN, this is n. This has nothing to do with the which dimension you are working on. So people might sometimes get confused that for 3 dimension represent this is 3, for 6 dimension this is 6, and so on. But that is not certainly true. We have to look into the group and then look into the value of the n for SUN, and then put that number here, and then follow the rule that horizontally increase by 1 unit, downwards decrease by 1 unit, and you calculate the numerator and denominator, you get 8. So 3 cross 3 bar is 8 plus 1, and this 8 is the adjoint representation of SU3. So in general, we have this n cross n bar, which we can write down as n square minus 1 dimensional representation plus a singlet, where n square minus 1 is nothing but the adjoint representation of the SUN. So in this way, we can employ and generically, the young tableau technique for SUN, also, but I have discussed on the method of the SUN, which is part of this course, to calculate the higher dimension representation starting from the fundamental or the lowest dimensional representations. And I think if you remember, practice this kind of thumb rules, you should be able to compute all possible higher dimensional representations for this given group. Okay, thank you.